So let's talk about ionic compounds. In this lesson, we're going to be writing chemical formulas and naming simple ionic compounds, as well as doing the same for multivalent or transition metals as well. So before we get into our lesson, you should be able to identify what an ionic compound is. And simply speaking, an ionic compound is made up of both metals and nonmetals. So the periodic table that's provided at the bottom of the slide might be helpful to you. So you will see that most of our elements on the periodic table are metals. They're in blue, and the nonmetals are in green. So I want you to take a second, pause the video, and see if you can identify which are the ionic compounds in this list. Okay, once you've done that, so you'll see here, this is an ionic compound, so is this, as is this, and this. And what's common about all of these is that they've got at least one metal and one nonmetal. And that's it. So when you're given a bunch of compounds at the end of this unit and asked to name them, this makes it easier because you can just have simple checks in your mind. If they have a metal and a nonmetal, you're talking about an ionic compound. All right, here's some information that I'm going to need you to know. If you don't already, I'm going to ask you to memorize this from this day onwards. So the first piece of information is the number of valence electrons. So the number of valence electrons in all of the elements in group 1 is 1. All of the elements in group 2 have 2 valence electrons. And then we're going to skip over groups 3 all the way to 12 and jump to group 13. In group 13, all of the elements have 3 valence electrons. In 14, they all have 4 valence electrons. 15 has 5 valence electrons. 16 has 6 valence electrons. 17 has 7 valence electrons. And group 18 has 8 valence electrons. Helium is an exception here, but we'll talk about that later. So the first piece of information that I'm going to need you to memorize is that along the periodic table, there is a trend in the number of valence electrons. The second piece of information that I'm going to ask you to remember has to do with the charge. So when an atom becomes an ion, they either gain or lose electrons in order to have a full outer shell. And there is a pattern that exists between all of the different elements in one group about what charge they form. And that makes sense because they've got the same number of valence electrons. So all of the elements in group 1 have a charge of +1. All of the elements in group 2 have a charge of +2. Again, we're going to skip over group 3 to group 12 and go to group 13. Group 13, all of the elements have +3. Now, group 14 is a bit of a weird one because we're not actually going to be looking at this or seeing this in ionic compounds at all. So we're going to skip over this one. If you really want, you can write the charge +4 or -4, but really, we're really not going to see any elements from group 14 in ionic compounds. In group 15, they have a charge of -3. Group 16 has a charge of -2. Group 17 has a charge of -1. And group 18, they're the noble gases. They don't form ions at all, so we can just call them 0. Again, we're not going to see these in our ionic compounds. Now, in order to make sense of the charge, all you have to remember is that it has to do with the gaining or losing electrons. Whenever electrons are gained, there's a negative charge. And whenever electrons are lost, there's a positive charge. So usually metals tend to have a positive charge and nonmetals tend to have a negative charge. So this information, both the number of valence electrons as well as the charge, I'm going to ask you to memorize from this point on. All right, so now that we have that information, let's actually do it. Let's start naming ionic compounds. So if I'm given a simple ionic compound like this, Li2Se, when you're naming them, we can sort of forget the numbers for now. So the first thing that we're going to look at is the metal, and the metal is always going to be written first. In this case, the metal is Li. I'm going to find it on the periodic table. And this periodic table is a little bit small, so you won't be able to see all the names. But if you pull out the periodic table that I've provided for you, it should be clear enough for you to see all of the names and the chemical symbols. So Li is lithium, so I'm going to write lithium out. So the metal name you have to write in full as you see on the periodic table. The next element that I see here is selenium, and selenium is right here on the periodic table. Selenium is a nonmetal, which means that I'm going to have to change the ending a little bit. And the ending of the nonmetal in ionic compounds is changed to IDE. So instead of it being lithium selenium, it's going to be lithium selenide. And that's it. I'm not writing anything about the numbers in my simple ionic compounds. I'm just leaving it as it is. So the compound that I'm given here, if I'm naming it, it's lithium selenide. Pause the video, do all of these. I'm going to take up the answers right now. So the first one is sodium sulfide. I've got aluminum fluoride. Calcium is the metal. I'm going to write the name of it in full. And phosphorus is my nonmetal. I'm going to change it to phosphide. Rubidium is my metal. And fluoride is my nonmetal. Sorry, fluorine is my nonmetal. I'm changing the ending to IDE. That's it for naming simple ionic compounds. Let's write chemical formulas for them. So this is a little bit more challenging, but you can still do it. So let's take a look at this particular compound. It's aluminum fluoride. Let's find where the two elements are on the periodic table. So aluminum is right here, and fluorine. So it says fluoride, but I know that we're talking about fluorine. Let's figure out where they are on the periodic table as we did. So aluminum is in group 13, and I know from my previous knowledge that the charge of aluminum is +3. I know that because every element in group 13 has this charge. Similarly, fluorine is in group 17. It has a -1 charge. All right, so let's write this information out. So what we're doing in chemical formulas is writing out this compound according to its element symbols. So aluminum has the symbol Al, and fluorine has the symbol F. And now what I'm going to do is write the charge along the top of here. So aluminum has a charge of +3, fluorine has a charge of -1. I'm going to change colors here. And now what's going to happen? So we're not done yet. So you've noticed that previously when we're talking about chemical formulas, you see a smaller number towards the bottom. What happens is that you're actually doing a switcheroo here. So what happens is that the charge of fluorine becomes the number next to aluminum, and the charge of aluminum becomes the number next to fluorine. So you should have Al F3. You might notice that I did not put the 1, and that's a rule in ionic compounds. Actually, not just in ionic compounds, when we're writing formulas in chemistry, if you have just one of a certain element, you can leave it without a number right next to it because that is inferred. So we know when we see an element that does not have a number next to it that we're only talking about one element. So this is the answer here. The chemical formula for aluminum fluoride is AlF3. Let's do some practice. So I want you to pause and then come back when you're done. So I'm going to take these up now. Magnesium and oxygen. So you know what? Let me just put the charges up here. I'm going to skip over group 14 just because I know that I'm not going to use it. Oops. -1. And I'm going to skip over group 18 as well because I'm not going to use that either. So Mg has a charge of +2, O has a charge of -2. When I crisscross these, I'm going to get Mg2O2. However, that's not quite right. So this brings us to another rule in writing chemical formulas for ionic compounds, is that if you have two of the same numbers right next to each other, or if you have two elements that started off with the same charge, you're not going to end up with both of those numbers right next to each other. So what's going to happen is that you're going to reduce to the lowest terms. So Mg2O2, I'm going to write it as MgO. And that would have been the same if, for example, the charge of magnesium was +3 and the charge of oxygen was -3. It would still be the same, right? You want to reduce to the lowest. So MgO is the answer here. The rest of these are pretty straightforward. So Li +1, S -2. When I crisscross these, I'm going to get Li2S, K +1, and -3. So cesium and bromine both have charges of +1 and -1 respectively. So I'm not going to write those numbers out because they're 1, right? And if you notice here, same with sulfur, right? Lithium had a charge of +1. When I brought it over, I didn't write a number 1. So you never write the number 1 when you're writing the subscript. All right, so we're done with the simple ionic compounds. We're going to take a look at our multivalent or transition metals, and that has to do with this particular section here. So I told you earlier to skip over groups 3 to groups 12 in terms of charge. So we're going to talk about that now. So what are multivalent or transition metals? They are metals that can form more than one kind of ion. So previously, when we talked about the charges in the particular groups, we noticed that, for example, oxygen always forms the charge -2. However, there are some metals that are found in the middle, and they're all metals, so you know they're going to have a positive charge. They can form more than one possible charge. So some of the examples that we're going to be looking at in class, or some of the elements that we're going to be looking at are, so for example, we've got copper. So this is the name. The element symbol is Cu, and these are the two possible charges that it can form. And we write them in their Roman numeral form when we're naming them. I'll talk about that. So 1, 2, and 3 in Roman numerals are pretty easy. 4 might be a little bit challenging, so just make sure that you know 4. So iron is Fe, lead Pb, tin Sn, gold Au. All right. So having gone over that, let's see if we can write the chemical formulas for this particular compound. Just like we did previously, we're going to need a periodic table, and I'm going to find copper on my periodic table. It's right here. So my element symbol is Cu. Chlorine, it says chloride, but I know we're talking about chlorine, is in group 17, Cl. The charge of copper, we don't know, right? Because this is a transition metal, but I always know the charge of chlorine. Because it's in group 17, it always has a charge of -1. Now, if we're looking at copper, according to my periodic table, I won't know what the charge is. However, if you go back to the name, you'll notice that there's a Roman numeral there. And that Roman numeral tells you the charge of the transition metal that we're talking about. So Cu +1, Cl -1, you still do the crisscross. Because they're both 1, I'm going to just leave them as CuCl. And that's it. Let's do more practice. I'm going to have a periodic table here. So similarly, CuCl. Cl, again, because it's in group 17, always has a charge of -1. Copper is right here, transition metal. How do I know the charge? I take a look at the name, and it always has to specify. So please make sure that you remember that when we're writing the name of it. If you're talking about a transition metal, you always have to specify the charge so the person looking at the name can properly identify which charge they need to look at. So crisscross these. There we go. So if you compare, copper 1 chloride had the formula CuCl, and copper 2 chloride had the formula, or has the formula CuCl2. So just because they're both the same metal doesn't always mean that they're the same charge when you're talking about a transition metal. So that's this big difference between what we were looking at earlier with what we're looking at now. Let's take a look at iron 3 phosphide. So iron has the element symbol Fe, as shown here. Phosphide, I know we're talking about phosphorus, so P. So phosphide, or phosphorus, always has a charge of -3. I'm going to write that there. And iron has a charge of +3. I know that because it says that in its name, so +3. So when I crisscross, I'm going to get Fe3P3, and the same rules apply from earlier because technically this is still an ionic compound. When I've got the same number, I can reduce it, so I'm going to get FeP. All right, let's do the opposite. So given a chemical formula, or given the chemical formula, I'm going to ask to write the name of the element. So I have CuCl here. So I know that the metal that we're talking about is copper. So I'm going to write that out. And I know that the nonmetal that we're talking about is chlorine. However, remember that when I'm naming ionic compounds, I'm changing the ending to IDE. So instead of chlorine, this becomes chloride. Okay, we're not quite done yet. And the reason we're not done is because this is a transition metal. Copper is a transition metal. And if you recall from earlier, we always have to specify in brackets what the charge of copper is. How can we figure that out? We have to do something called reverse crisscross. So we don't see any numbers here, which tells us that the numbers are 1, right? So we never write these, but we know that we're talking about 1 Cu and 1 Cl. If we can take those numbers, or if we reverse our process and take it back, you can guess that the number for copper is +1. You can guess that the number for Cl is -1. So with this information, that tells me everything I need. So chlorine, right, always has a charge of -1. That makes sense. And copper, according to this, in this particular compound, has a charge of +1. And that's it. That's how I name this compound. Let's do a few more examples. So just as we saw earlier, FeO. And because I don't see any numbers here, I'm going to assume that this is 1. And let's reverse our process. So notice I'm adding the positive and the negative. The metals always have a positive charge and the non-metals always have a negative charge. Now, so this is telling me that iron has a +1 charge and that oxygen has a -1 charge. Based off of what we know on the periodic table, something is wrong here. So I want you to take a look at oxygen. It's in group 16. It should have a charge of -2. And in fact, it always does have a charge of -2. So this is not quite making sense. So what might have happened here? So remember that oxygen always has a charge of -2. And iron, we don't know what the charge is. If these two crisscrossed, and then they ended up so that the charges were reduced to its lowest form as an FeO, we know that the charge of iron must have been +2. So we're working backwards here. So let me just repeat that one more time. So if I did my reverse crisscrossing with the information that I'm given, I realized that oxygen would have had a charge of -1. However, I know that that's not true. Oxygen always has a charge of -2. Now, given this information, and given the fact that in the end, there are no numbers here, and that both of them became 1, that tells me that the charge of iron, the number of iron at least, was the same as the number of the charge of oxygen. So both of them had to be 2. So when I'm naming this compound, so the name here, so I know that the element, so the metal is iron, the non-metal is oxygen, so I'm going to change the ending to oxide, and in brackets, I'm going to write the charge. Because I know that both iron and oxygen ended up canceling out, the charge of iron has to be 2. Right? Just by looking at it, you might not always guess it, but you always have to go back and check the charge of the non-metal to make sure that it is correct and as we know it. So let's see here. We've got Fe2O3, and we can just try and reverse our crisscross. So here, according to this tells me that iron has a charge of +3. And if I reverse this tells me that oxygen has a charge of -2. And that's right. It always makes it oxygen does have a charge of -2. So this charge is also right. So iron, oxide, and the charge, according to this, is +3. So the only difference, the only extra step that we require is in case the elements had to be reduced, right? So in case the numbers had to be reduced in that compound, that's the only scenario where it becomes harder for us to figure out the charge of the transition metal. But other than that, we've covered all of the topics. So writing and naming chemical formulas for simple compounds, as well as writing and naming chemical formulas for ionic compounds that have transition metals or multivalent metals. And that's it.